Good day and welcome back to today's STS-134 Utilization Flight 6 briefings. This is the mission overview briefing featuring Gary Horlacher, who's the lead for the space shuttle portion of the mission, and Derek Hausman, who's the lead for the space station control team for this flight. And we'll start out with our opening statements and then move on to your questions. Gary?
Thank you, Kelly. Well, good morning, everybody. It's great to see you all here today. Really appreciate you taking some time to come hear some of the details of the final voyage of Space Shuttle Endeavour. STS-134 ULF-6 will be the 134th mission for the Space Shuttle program. It will be the 35th shuttle flight to the International Space Station, and it will be the 25th and final flight of Endeavour. We've got an exciting mission planned out, so let me go ahead and introduce the crew to you. If we can get the crew photo up, please. So we'll start in the center bottom there. You'll see our Commander Mark Kelly. He is a veteran space flyer of 3 previous shuttle flights, STS-108, 121, and 124. He's a captain in the U.S. Navy, and this will be his second flight on Endeavour. Move to the left side of the picture there. We'll start on the left and move to the right. We've got our pilot, Greg Johnson. He is a colonel in the U.S. Air Force, and he has flown once before in STS-123. That was also on Endeavour. And Greg will also be one of our lead robotics crew members on board when we get to orbit. Next to Greg is Mike Fink. He is also a colonel in the U.S. Air Force. He's a veteran flyer of 2 expedition missions to the International Space Station, Expedition 9, as well as Expedition 18, where he was the commander. This, however, will be his first flight on the shuttle. Both of his expedition flights were on Soyuz vehicles. Next to Mike is Greg Shamatov, MS-2. He also spent a long-duration mission on the space station with Expeditions 17 and 18. And his ride to and from the space station for that mission was on board the shuttles as well, but this will be his first full shuttle flight on Endeavour. Next to him is Drew Fustel, MS-3. He was last at the Hubble servicing mission on STS-125. Doing numerous spacewalks, and he will be one of our lead spacewalkers for this flight. And on the far right there is Roberto Vittori. He's our European Space Agency astronaut on this mission. And he did 2 Soyuz taxi rotations to the space station, one back in 2002 and another in 2005. And this will be his first flight on the shuttle. So if we can go on to the crew patch, I'll go ahead and tell you the description of the patch here. The design of the 134 crew patch highlights research on the International Space Station, focusing on fundamental physics of the universe. On this mission, the crew of the Space Shuttle Endeavour will install the Alpha Magnetic Spectrometer, the MS experiment, which is a cosmic particle detector. By studying subatomic particles in the background cosmic radiation and searching for antimatter and dark matter, it will help scientists better understand the evolution and properties of our universe. The shape of the patch is inspired by the International Atomic Symbol, representing an atom with the orbiting electrons around the nucleus. And the burst in the center refers to the Big Bang Theory and the origin of the universe. Space Shuttle Endeavour and ISS fly together in the sunrise over the limb of the Earth, representing the dawn of a new age, understanding of the nature of the universe. So I think it's a very representative patch for the complement we have executing on this flight. Next, I'd like to introduce you to the Space Shuttle flight directors that will be supporting the mission. If we can get the ascent photo up there, Richard. Richard Jones will be our ascent flight director. He's a veteran flight director, has many ascents and entries under his belt, and he'll also be serving as the Shuttle Team 4 flight director. If any issues come up during the mission that we need extra support on, he'll lead that team as well. I will be the Orbit 1 flight director. I'll be working with the crew from the time they wake up in the morning till about halfway through their workday. And then I will hand over to the Orbit 2 flight director. You see a picture of Paul Dye here. He is probably the most senior flight director in our office. You've seen him many, many times, both as a lead and as an Orbit flight director. And he's also a space station flight director as well. And he will be working from middle of their crew workday right up to the time they're going to sleep at night. Then he will hand over to the Orbit 3 planning flight director, and that'll be Kwatsi Alabarujo. And Kwatsi's another veteran flight director. He's certified both station flight director side as well as shuttle. And he will be taking care of Endeavour while the crew sleeps at night, and also replanning the activities for the next day if any adjustments need to be made. He will also be the lead flight director on the next mission, STS-135, so you'll see him again very shortly. And near the end of the mission, we'll be bringing Tony Sacacci and his team, entry team, on to replace my team, the Orbit 1 team. They'll come in and take care of standard landing minus 1 day activities to make sure the flight control system and all the landing subsystems on the orbiter are ready to bring Endeavour home. And then they'll come in and go ahead and land Endeavour, hopefully a beautiful landing right at KSC, right on time. So STS-135 ULF-6, ULF is a utilities and logistics flight to the space station. The assembly of the space station is, for all practical purposes, complete. So we will be hauling up quite a bit of cargo, 2 very large payloads to be installed on the station, as well as a bunch of cargo to be transferred inside. This is a 14 plus 1 plus 2 day mission, which means we got 14 nominal days planned. We also have the consumables available to add an extra dock day to the mission if a need arises. And then the plus 2 days at the end gives us some opportunities to bring Endeavour home safely, hopefully to KSC, usually talking about weather challenges there. We also have 4 spacewalks planned, 2 very large payloads that will be installed robotically on this mission. And then we also have a unique test objective that we're going to fly this flight. And that's going to be for the Orion program. So I'd like to take a few minutes to introduce you to some of that hardware. This test is going to be called the Sensor Test for Orion RELNAV Risk Mitigation. I know that's a mouthful, so we're going to download really quick to a NASA acronym, which we all love, and that's STORM, S-T-O-R-R-M. And this system is basically a visual navigation system, and it will be used for uncrewed and or crewed dockings and undockings for future spacecraft. And the tests we're going to perform on this flight will both demonstrate and characterize the performance of this system in the actual space flight environment that it's going to be expected to perform in. And that's important because all space flight hardware gets designed on the ground, tested the best we can, but you really can't simulate the entire space environment here. So until you get it to orbit, there's only so far you can take it, and technology goes through what's called technology readiness levels. And so you get through a certain stage here on ground testing, you go as far as you can go, and you can't increase the readiness level of the hardware until you get it into the actual environment, which is up in space. So this is really exciting to get this hardware up in space, give Orion a chance to check it out before they're actually going to be depending on that to do a rendezvous and docking. So if I can get the first still photo here and start explaining some of the hardware to you. You see the sensor enclosure assembly. This is installed in the payload bay, and I'm going to show you the actual locations in just a minute. But it contains the 2 sensors that the STORM system is comprised of, the first being the vision navigation sensor. And this is basically a LiDAR-based system, which means light detection and ranging. It's an optical sensing technology, and it measures the properties of reflected light to determine target information. It's similar to standard radar, except it uses laser pulses instead of radio waves. The VNS acquires a complete 3-dimensional image of the target in a single laser pulse. And one of the most impressive specs, in my opinion, is the acquisition range is about 20,000 feet or 6 kilometers. This is about 3 times the capability of the shuttle trajectory control sensor that we use in close flying with the orbiter. The other sensor inside that same enclosure is the docking camera. This is a high-resolution visual camera that a crew member could use for both situational awareness as well as piloting cues if he is manually flying the ship. And for comparison on this hardware, it's about 16 times higher resolution than the shuttle centerline camera that we use today. I can go to the next still picture of the avionics box. This is also mounted in the payload bay, and it provides basically power distribution both for the sensors and the avionics box itself. It takes care of the data recording. The sensors are going to collect a tremendous amount of information, so it'll record and store that data inside this enclosure as well. And it's also the interface between the laptop. There's a dedicated Storm laptop that'll be in the crew cabin. And Drew is going to be our prime crew member operating that laptop in the Storm system for us. So he'll activate it and get it all set up for the activities. And then he'll be there to monitor and help us troubleshoot if anything were to crop up that needs some attention. And then next slide here, you'll see another key component of this system are the Storm reflectors. On the right side, you got a picture of the docking mechanism on the space station that the shuttle docks to. And circled in red there is the actual docking target. And a bigger picture of that there is on the left side. And you can see on the outside perimeter of the docking target circled 4 of the reflectors that are mounted there specifically for the Storm DTO. And in the center, this picture doesn't show the crosshair that's normally mounted there for the actual docking. And on that crosshair will be the 5th element as well. So there'll be 5 reflectors installed on the docking target for the Storm system to utilize for the approach and docking and undocking. So if we go to the last slide on Storm here. So as I said before, the VNS system is going to acquire a 3D image of the target in a single laser pulse. And this reflected pulse allows for range or distance determination and intensity of the return signal to be determined. So many pulses over time allows you to also determine range rate or relative velocity between the 2 spacecraft. The pattern of reflectors in the image allow for the determination of relative vehicle orientation. So if you look down at the bottom there on the left, you see a visible image of a docking target mounted on a stand here on the ground. The next picture over, the intensity image, you can see basically all blue. It's kind of hard to see there, but very specifically you can see the 5 red dots where the reflectors are. That's because the return signal from those reflectors is much more intense than the reflected signal from the surrounding surfaces. So the system has a knowledge of where those reflectors are and then can do some computations to determine the relative orientation, which is critical for docking 2 spacecraft. So all these images will be processed to identify the target's determination of its range, range rate, attitude, and bearing. All these are critical parameters to allow for a successful docking of 2 spacecraft. So we're really excited about having this Storm test on this flight, and it's also going to allow Endeavour to fly a very unique trajectory on undocking day. We'll talk more detail about that in just a little bit. So now I'll go ahead and give you an overview of the payload bay of the orbiter, if I can get the payload bay video rolling here. There we go. So in the front of the vehicle, you're going to see the orbiter docking system, which allows us to actually dock and mate with the space station. On the starboard sill of the payload bay is the orbiter boom sensor system that we use for the TPS inspections. On the opposite port sill there is the shuttle robotic arm. And here in the front of the ODS, along the truss, is the sensor enclosure assembly for the Storm. That's where the 2 sensors are located. And then on the port sidewall there in Bay 3 is the avionics enclosure. That's the 2 pieces of hardware in the payload bay for Storm. In the center of the payload bay is the Express Logistics Carrier 3. It's going to have a lot of spare parts for space station. And in the back is the AMS. That rounds out the cargo bay. So with that, I think we'll go ahead and walk you through day by day through the mission, give you the highlights of what we're going to be accomplishing each day. Flight day 1, of course, is dedicated to getting Endeavour into space, get her off the launch pad, and Richard and his team will get her accelerated to 17,500 miles an hour, and then get set up for orbit operations, convert the vehicle from a launch vehicle to orbital spacecraft. As soon as we get to orbit, crew members throw a couple switches, allow Endeavour to provide power to the AMS payload, and then the ground team here in Mission Control for the AMS folks will go ahead and start to activate and check out the AMS payload and make sure that the ride to space did not cause any issues with the payload. And they'll work that activation and checkout for the first couple days of the mission. We'll also go ahead and a couple crew members will get the shuttle robotic arm, take it out for a short test drive, do a checkout of it as well to make sure it's all ready to go for the inspection on flight day 2. And then the end of the day, we'll wrap up with our standard downlink of all the imagery taken during the ascent of the external tank, umbilical well pictures, et cetera. Get that down to the ground team to start analyzing as quickly as possible to see how we performed during the ascent. Flight day 2, of course, is going to be our standard TPS inspection day. I think we'll roll a video here and show you the robotic operations involved in that. Shuttle arm will come on over to the opposite side of the vehicle and pick up the OBSS. And move out to the starboard wing and do a quick, it's called a flat field survey. Take a quick look at, we'll look at the ohms pod there first, since we're in a good position to do that. And then we'll do a quick flat field survey, allowing the ground team to calibrate the sensors, and then we'll pick up with the start of the wing survey. We'll be picking up detailed information on the RCC panels on the leading edge of both wings, as well as the nose cap. And these are the areas that receive the highest temperatures on the re-entry and return to Earth. So I want to make sure that no damage occurred to those panels on the ride up to orbit. So there we're finishing up the nose cap. We get on the port side. We'll do our racetrack motions, go up and down the wing to make sure we capture all the surface area. And we'll pause here and take a quick look at the T0 umbilical on that side of the vehicle, as well as that ohms pod, make sure there's no issues there. And then we'll pick up and complete the port wing survey. And of course, the ground team will start analyzing this data as quickly as we can get it to the ground. Some of it comes down in real time, and the rest of it will downlink as soon as the inspection is complete. And hopefully everything will go well, and they'll get all that data analyzed and turned around and clear the vehicle by flight night 3. So with the inspection complete, the arm will go ahead and put OBSS back into its carriage on the starboard sill and release it. And then we'll go ahead and take advantage of this to grapple the ELC payload and stay in that config and be ready to install the ELC right after docking. A couple other activities we'll accomplish on flight day 2 will be a couple of the spacewalkers will check out their spacesuits, make sure everything's looking good there, be ready to transfer those over to the space station to get ready for the 4 spacewalks. And then the rest of the key activities for the day will be checking out some of the rendezvous systems for the rendezvous on flight day 3. That'll include centerline camera installation, the orbiter docking system ring extension, rendezvous tools checkout, and for this flight we'll do a storm tools checkout. Drew will get the storm laptop out, get that software fired up, and take a look at the system, make sure everything looks good there. And that'll lead us into flight day 3, the rendezvous day. The storm system will go ahead and be turned on and ready to start supporting at its acquisition range of about 20,000 feet. And we'll start a video here which occurs inside of that range. So the video starts here just underneath space station. We're just about 600 feet out and get ready to start the RPM maneuver, the rendezvous pitch maneuver. Commander Kelly will halt the vehicle's approach at this point, get the initial conditions set up, and then kick off the RPM. And you'll see the flashes here are indicative of the space station crew members taking a lot of very high resolution digital images of the entire surfaces of Endeavour as it does its complete backflip. And again, this information will be downlinked to the ground as well for the engineers on the ground to analyze and verify that everything on the vehicle looks good. Once that RPM is complete, Mark will go ahead and set up the right conditions and fly Endeavour up in front of the space station on what we call the V-bar. It's a velocity vector that the space station's flying in. Halt our approach there and get set up to start the final approach into the docking port. And as he's flying in, he'll take a good close look at the vehicle's alignment. If any adjustments are required, he'll stop at 30 feet, make those adjustments, and then push in for the final approach and docking at the space station. Okay, and with that, we'll go ahead and get the hooks driven, get the 2 vehicles securely mated together after all the motion is successfully damped out. And then we'll go ahead and open the hatches. The crews will greet each other, and we'll do a quick safety briefing so the shuttle crew is up to speed on any emergency response actions they might have to take while they're docked to the station, and then it'll be time to get to work. At that point, I'll turn it over to Derek to talk about the activities we'll accomplish during the dock time frame.
Okay, thanks, Gary, and good morning, everybody. It's a pleasure to be here today to talk about what I expect to be a very exciting and very challenging mission. Gary and I have been working on preparing for this mission for a number of years, so it's pretty gratifying and pretty exciting to be this close to launch. Before I pick back up with the Flight Day 3 with the mission overview, I'm going to first talk about the flight directors that are going to be staffing the mission on the space station side. I'll be the Orbit 2 or lead flight director for this mission, and the Orbit 2 shift is aligned basically with the last half of the crew day, and on EVA days my team will be on console. I'll also be on console for the AMS installation as well as the ELC-3 installation. Dana Weigel is going to be the Orbit 1 flight director. You can see a picture of Dana there. She was selected as a flight director in 2005. She was the lead flight director for the STS-134 1JA mission, so you may recognize her from previous briefings that you got here. She was also my Orbit 1 flight director on my last lead, which was STS-120. So Dana and I have worked together a number of times, and I look forward to working with her again on this mission. As the Orbit 1 flight director, she and her team will be on console for the first half of the crew day, which means on EVA days, she and her team will be responsible for getting the crew prepared for the EVA and then out the hatch, at which point the Orbit 2 team comes on. The Orbit 3 or planning flight director on the station side will be Dina Cantella. Dina is one of the newer flight directors in the office. She was selected in 2008. She's done a large number of increment shifts on console for the space station, or the shifts between shuttle flights, but this will be her first space shuttle assembly mission. And then finally, Dave Korth is going to be the Team 4 flight director. And as Gary mentioned, Team 4 is basically a resource that we have in place before the mission that can work off console any kind of additional analysis or assessments that come up during the mission. So in theory, if it's a smooth flight without any surprises or failures, David won't have a lot to do, but that's typically not the case when you go into something that's complicated. So those are the station flight directors that'll be supporting and working with me and their teams to make this mission happen. I'll now talk about the Expedition 27 crew that will be on the space station when 134 arrives, if we could get that still up there. Starting on the right in this picture, you can see the commander of the space station, Dmitry Kondratyev. To his left is Andrei Borisenko. Next is Katie Coleman, who will be one of two U.S. crew members on the station at the time of 134, and Katie is actually on board right now. Continuing to the left is Alexander Samokotayev, then Paolo Naspoli, who's the European Space Agency astronaut, will be on board for 134 and is actually on board today. And then finally on the far left is Ron Guerin. Dmitry, Paolo, and Katie arrived on the station December 17th of last year, and they're scheduled to come home May of this year, May 2011. Andre, Alexander, and Ron Guerin are scheduled to arrive on station April 16th, so early next month, and they're scheduled to come home on September 2011, September this year. And as has been the case in past shuttle missions, we rely quite extensively on the station crew to help us with all of the activities associated with the mission. Specifically, the station crew assist in all the space station robotic arm activities, lending their expertise and support for those activities. We also depend on the space station crew to help us prepare the crew, the EVA crews on the morning of EVA days, and then to configure post-EVA on EVA days. In addition, they help with the transfer activities and a lot of the science that we're going to be doing. And if I could have the next still, I'll give you a quick update of the current configuration of this station as it will be as 134 approaches and docks. You can see the two Soyuz spacecraft. We expect to have a Progress attached, and we also expect to have ATV-2 attached to the station. You will notice that this does not show HTV. The expectation is that the HTV will be unberthed and deorbited on March the 28th as planned, despite the challenges, of course, due to the events in Japan. Next still, please. Just basically a shot with Endeavour docked to the space station. One interesting thing that will become clear as I talk through the subsequent mission days, and specifically the EVA days, we're doing work up and down the truss. We're doing work on the port side of the truss in terms of ammonia coolant loops and the ELC-3 installation. We're doing work on the starboard side of the truss with the AMS installation, and also the installation of the orbiter boom sensing system, or OBSS, on the truss. So a little bit different than previous flights where we had generally an area of focus. For this mission, we've got 2 major payloads that we'll install robotically, and then we have EVA tasks that take us up and down the station truss. And next, I'll talk in more detail about the 2 primary payloads that we have in the orbiter payload bay, which Gary introduced you to. First, I'll talk about Express Logistics Carrier number 3, or ELC-3, if I could have the still. Excuse me, the video. And we've got a number of spares on ELC number 3, which are depicted here. See, first we've got a cargo transport container, or CTC, which has a number of spare electrical power components. We have one of 2 S-band antennas. We have a SPDM arm, a spare arm on the ELC. On the opposite side of the ELC, we have an ammonia tank assembly, which can be used to support the external ammonia cooling loops. We have a high-pressure gas tank with high-pressure oxygen for the airlock. We have a payload that comes up on the ELC, the Space Test Project. And finally, we have the second S-band antenna assembly. So a number of critical spares that are intended to support the station as it continues its operation post-shuttle. Of course, the other major payload in the payload bay you heard about quite extensively in the previous briefing, and that's the Alpha Magnetic Spectrometer, AMS-2. I've got a still here of the processing at KSC, and then I've also got kind of an overview of the key components of the AMS. And because of the detail that you got in the previous briefing, I won't spend a lot of time talking about the operation of the AMS, but suffice it to say that everybody is extremely excited about the opportunity that we have to launch and activate this payload, and there's tremendous expectations in terms of the science and the research and the knowledge that we're going to get from AMS. Okay, with that, I'll move back into the flight day overview, picking back up with flight day 3, where Gary left off. After the hatches get opened, the crews get acclimated, they get their safety briefing. We hit the ground running with the ELC-3 unberthed from the shuttle payload bay and installation on the truss. And I've got a video depicting that operation. You can see the payload being pulled out of the payload bay using the shuttle arm, and that'll be Fink and Vittori operating the shuttle arm. They translate the payload to a predetermined handoff position, and they stop there. At that point, Greg Johnson and Greg Shamatoff then grapple the ELC-3 with the station arm, and then they carefully maneuver ELC-3 to its installation site on the space station truss. And one thing that's a little bit different about both the AMS and the ELC payloads is that there's no additional activity required to make the connections. That connection is automatic and remotely controlled once it gets installed on the truss. You'll see here the mobile transporter with the station arm attached, then translates to the work site that's required for the next day's activities, which is AMS install. And once we finish ELC-3 install, that's basically into flight day 3. Flight day 4 begins our AMS activities, and I've also got a video here that shows you that. For AMS installation, Foystel and Vittori will be operating the shuttle arm, and similar to ELC-3, we use the shuttle arm to extract the payload from the shuttle payload bay. We maneuver it to, again, a predetermined handoff point, at which point Greg Johnson and Greg Shamatoff, again on the station arm, maneuver the arm in and grapple the AMS payload. Once that's complete, the shuttle arm backs off to a viewing position to give us good views of the AMS install operation on the port side, the starboard side of the truss. And at that point, Johnson and Shamatoff carefully maneuver the AMS to its installation site on the truss. And again, this is in terms of the power and the data connections and the actual capture of the payload on the truss, this is a completely remotely controlled operation that's controlled by the crew inside the space station, as well as by ground controllers. So no EVAs, cables are required to support either of those activities. Then you can see the mobile transporter with the station arm attached, then translates to the next work site required to support the next day's activities. So at the end of the flight day 4, we've got ELC-3 installed on the truss, receiving power and data. Flight day 4, we've got AMS installed on the truss, power applied, and at that point, the AMS collaboration, who's going to have a team in mission control, will begin all their activation and checkout activities on the AMS. Moving on to flight day 5, I'll start talking about our spacewalks, our EVA plans for the mission. And I'll say up front that you'll get a detailed briefing coming up next from our lead EVA officer, Allison Bollinger. So I'm not going to go into a lot of detail about the EVAs and the sequence, but I'll hit the high points and help you guys understand what the primary objectives are. EVA 1 will be conducted by Feustel and Shamatov. Drew, as Gary mentioned, has conducted previous EVAs during the last Hubble servicing mission, and this will be Greg Shamatov's first EVA. Overnight, between flight dates 4 and 5, the crew slept in the U.S. airlock doing what we call the camp-out pre-breathe protocol. So the night before, when they went to bed on flight day 4, the crew is buttoned up in the airlock. We close the hatch. We reduce the pressure to 10.2, and then they breathe an oxygen-rich environment overnight in order to purge nitrogen from their blood and tissue. When they wake up on flight day 5, they're ready to go. We open the hatch, bring the pressure back up to the nominal pressure of 14.7, open the hatch, let them do what they need to do in the morning, and then we start getting them suited up. There's 2 primary objectives on EVA 1, the first of which is the Materials International Space Station Experiment, or MISSE experiment. And this is the next in a series of experiments that are sponsored by the Department of Defense that look at the effect on materials over time of space environments. We're first going to retrieve 2 MISSE payloads that are currently on space station, MISSE 7A and MISSE 7B. We go out to ELC-2, which was installed when we arrived. We pull off the MISSE 7A and 7B. We bring those payloads, install them in the payload bay. Then we pick up MISSE 8, which is the next in the line of MISSEs, which we brought up on this flight, plug it in on ELC-2. The other primary objective on this EVA is to set up for an ammonia fill activity on EVA-2. And I'll just give you a little bit of background. Each of the power modules on the space station has an ammonia cooling loop that runs continuously and keeps the batteries and other components on the power channel within limits. This P6 PVTCS, which we're going to service on this mission, has a slow leak that over time could cause the loss of that loop, probably 1.5 to 2 years, potentially, depending on how the loop behaves. So what we're going to do on this mission is we're going to top off that PVTCS ammonia cooling loop such that we extend the life. Ideally, if the fill goes well, we're going to extend the life a number of years. So what we do on EVA number 1 is start the setup for the actual ammonia fill on EVA 2. We route ammonia coolant lines. We vent a nitrogen pad that's in that line to protect the line, and then we basically set up the pipeline that we're going to use on EVA 2 to make that to do that ammonia fill. And again, you'll have more detail about that during the EVA briefing coming up. We also on EVA 1 install a couple of antennas on the external surface of the lab, and those antennas are going to allow payloads and hardware on the external portions of the truss to communicate wirelessly, have basically data transmission between those payloads, the payloads and hardware on the truss to computers inside the space station. So those are the major objectives of EVA 1, and estimated EVA duration, as it is for all the EVAs, is 6 hours and 30 minutes. Okay, we can go to the next day, which will be flight day 6, of course. We start off flight day 6 with OBSS grapple and handoff, and I've got a video portraying that here. For this activity, Greg Johnson and Katie Coleman this time will be operating the station arm, and they will remove the OBSS from the payload bay. They'll present it to the shuttle arm operated by Feustel and Vittori, and Drew and Roberto will use the the shuttle arm to grapple the OBSS, which is the config that it'll stay in for the next several days. Flight day 6 is the day that we preserve time for a focused inspection if required. That's a typical thing that we have done on all the recent missions. Basically, if there are areas of interest or anything that the analysts on the ground need to look at more closely based on the data that was gathered early in the mission, we would use the OBSS, or the Orbital Boom Sensor System, to go take a look at those areas of interest. The likelihood is that we won't need that time, but we've got the time available on this day if we do need it. The other things we do on Flight Day 6, we do work in some well-deserved off-duty time for the Endeavour crew, since they've been working pretty hard up to this point. And then we start the preparations for EVA number 2. So we get all the tools required for EVA 2 gathered, everything configured properly. We do a final procedure review, look at the last details, see if anything's changed from what the pre-flight plan was. And then EVA 2 will be conducted by Drew Feustel and Mike Fink. And then they, at the end of the day, we put them in the airlock and they start their camp-out activities. Flight day 7, we wake the crew up, and Drew and Mike come out of the airlock and do what they need to do in the morning, eat breakfast, etc. And then we start the EVA off for EVA 2. The plan is to have Greg Shamatov inside as the IVA. I didn't mention on EVA 1, Mike Fink will be inside as the IVA, and basically the IVA is the astronaut inside the space station that has the detailed procedures for the EVA, and he's the choreographer, or basically the leader of the EVA. He steps the EVA crew through all of their activities and does all the coordination with the ground as the crew works through their tasks. The primary objectives on EVA 2 are, again, as part of this PVTCS, or ammonia cooling loop fill that I mentioned during EVA 1, we did the prep for. For EVA 2, we actually do the fill. We flow ammonia through these lines that we pre-configured on EVA 1, and we transfer approximately 6 to 8 pounds of ammonia from an ammonia tank assembly that includes a reservoir of ammonia to the leaking PVTCS loop. In addition to the ammonia operations, we also perform a lubrication operation on the port Solar Alpha rotary joint, or port Sarge. And this lubrication operation is similar to what we've done over the past several flights. Some of you may recall that we had an issue with the Sarges in that there was damage being done to the race rings, which was affecting their performance, which causing unacceptable vibration. We've developed a technique by which we can lubricate those Sarges in order to fix that problem and avoid additional damage in the future. So what we're doing on the port Sarge here is basically a precautionary measure to head off any problems we might have in the future with this Sarge. Once the fill is done, we have to do ammonia venting during this EVA. So we flow the ammonia from the ammonia tank assembly to the leaking loop. At that point, we close valves, open QDs, but then we've got ammonia isolated in some of the lines along the truss with no pressure relief, basically. So once we completed the fill, we're going to do 2 ammonia vents that clear ammonia from the lines that we use to fill the leaking loop. And finally, the SPDM latching end effector, we're going to do a lubrication activity on the SPDM LEE, or latching end effector. And what that involves is actually presenting the SPDM LEE to an EVA crew member with the SPDM on the end of the station arm. The crew member performs that lube, and then the SPDM backs off. Again, you'll get details in the next briefing. But EVA 2, again, is estimated at the nominal time of 6 hours and 30 minutes. Okay, moving on to Flight Day 8. Flight Day 8 will be a prep day, of course, for EVA 3 occurring the next day. We're also going to work in some more off-duty time for the crews. We'll do the tool configuration for EVA 3, and then we'll do EVA 3 procedure review. And normally, this is the day at which we'd put the crew in the airlock for what I call the camp-out protocol, which is what we did on EVAs 1 and 2. For Flight Day 8, we are testing out or trying out a new pre-breathe protocol. What it's referred to as the in-suit light exercise pre-breathe protocol, or ISLE for short, ISLE. And the difference with this protocol is that it doesn't require the overnight camp-out that I described for EVAs 1 and 2, and that were used for most of the previous EVAs on the last several flights. So, in terms of complexity, in terms of the quality of life of the crew, this aisle protocol is a pretty significant upgrade, because we don't have that point the night before where the two EVA crew has to go in the airlock and we shut the hatch, and they're forced to spend the night overnight in the airlock. With this in-suit light exercise or aisle protocol, the night before the EVA looks exactly like any other night during the mission. They wake up, they don't have to stay on the portable breathing apparatuses, they don't have to stay on the oxygen masks. So up until the point where they actually begin the EVA prep on the morning of, it looks just like any other day. The other issue that some of you folks may be familiar with is that during campout, when we have the airlock at 10-2, there's failures on the station that can automatically repressurize the airlock. And we've had that occur at least once, probably more than that, on previous missions. With this in-suit light exercise protocol, you're not exposed to that, because the spacewalking crew is at a normal pressure going through their normal routine. So we think this is an improvement. We think this is an improvement over the campout protocol. And of course, the main thing we're after here is crew safety. We're trying to, all of these protocols are designed to prevent the bends. So of course, leading up to this, we put the aisle protocol through all the standard medical reviews and tests that both the campout and the exercise pre-breathe protocols have been subjected to, and everybody's comfortable that it's completely safe, and we think it offers some significant advantages over the campout protocol. So flight day 9 will be Drew Feustel and Mike Fink performing the EVA number 3, and we'll have Greg Shamatov inside the space station orchestrating the EVA as the IV or IVA crew member. The primary objectives on EVA number 3 are first to take a power data grapple fixture, or PDGF, which is the base from which the station robotic arm operates. We're going to take a spare PDGF from the U.S. side of the space station. We're going to translate that hardware to the FGB, and we're going to install that power data grapple fixture on the FGB. In addition to the structural installation, we'll do a power and data installation so that FGB PDGF will be as functional as the grapple fixtures on other places on the U.S. segment. Once that task is complete, we'll have at least the option in the future to use the station robotic arm based on the FGB for any task that may be required in the future. Second major objective on EVA-3 is the rewiring of some of the external cables that route power from the U.S. segment to the Russian segment. I mean, we've had the capability basically from the beginning of station to route extra power not required on the U.S. side to the Russian side in order to augment their capability, their power produced by their arrays. As it exists today, the wiring and the channelization is not optimal, in that a single failure on the U.S. side can have a significant impact on the Russian segment. What we're doing on EVA-3 is rewiring that connection such that we're not as susceptible to failures. In other words, we're going to have a failure on the U.S. side, and the impacts on the Russian side will be significantly minimized. So it's an enhancement, but it's a significant improvement, and it improves our ability to withstand failures in the future. Let's see, and those are the two major objectives on EVA-3, and again, nominal 630 duration on EVA-3. And one other comment on the in-suit light exercise protocol. The plan is to use it for EVA-3, and then at the end of the day, we're going to have a conversation with the crew and also a tag up with the flight controllers to talk about how it went. Were there any surprises? Was there anything that didn't work as we expected? Is there a reason not to go do it for EVA-4? If everything turns out well, if there were no surprises, no issues encountered, the plan will be to use that in-suit light exercise protocol for EVA-4 as well. If there were surprises or there are things we're not comfortable with, we'll just download to the camp-out protocol for EVA-4. And that takes us through flight day 9. Moving on to flight day 10, we are, as probably many of you know, we're leaving the OBSS, or the boom, on station during this mission. So because we're doing that, the orbiter needs to do their late inspection that they normally do post-undock during the docking period. Flight day 10 is the day we're going to do that. and I'll hand back to Gary to talk about the details of that.
Okay, so we'll go ahead and do a dock late inspection on this flight day. And we have done this once before back on STS-123. Of course, the space station was in different configuration back then. And so you see the animation going on here where you can see the GEM module right above the shoulder of the shuttle arm. And some of the other station components kind of constrain the space we have to work in. So this is a unique trajectory and procedure to do this. We actually did execute this on orbit on STS-131 due to their KU band antenna failure. So we have run it on orbit, and we'll be flying the arm exactly the same way as we did on that mission. We have made a couple improvements with camera views, etc. But otherwise, this will be the second time we're running this procedure. So we got part of the starboard wing taken care of. Here you see the nose cap. And then we come on over to the port wing. And it turns out this procedure and data collection is very, very close to the capability that we have on both Flight Day 2 and the nominal undock late inspection. But with some of the constraints of the space station hardware, we are going to be just a little bit shy of what we normally get. But again, the data on STS-131 was very good, and the team was very pleased with the results, so we'll be doing that again here. So back to you, Derek.
Okay. Continuing on with the Flight Day 10 activities, we're going to do preparations for EVA-4, of course, standard pre-EVA stuff. We're going to get the tools configured. We're going to get the procedures reviewed. And the spacewalkers for EVA-4 will be back to Mike Fink as EVA-1, so this will be his first shot at EVA-1, and he'll be executing EVA-4 with Greg Shamatoff. Moving on to Flight Day 11, early in the day we're going to do the hand off the OBSS from the station arm to the shuttle arm. I've got some video here that shows that. And Greg Johnson and Katie Coleman will be operating the station arm, and they'll maneuver to a point where they can grapple the OBSS on the grapple fixture basically in the center of the boom. Once the OBSS is grappled by the station arm, the shuttle arm will back off and then maneuver to a viewing position. And the goal here is to maneuver the OBSS on the station arm to a point near enough to the S1 truss that the spacewalkers can then take the boom from the station arm and then install it on the S1 truss. And again, in terms of major objectives for this EVA, the goal is to stow the OBSS on the station truss, on the S1 truss. The reason we're doing that is because we can use the OBSS to significantly extend the station arm reach. And folks who are familiar with STS-120 and the solar array repair that we ended up doing on EVA-4 know that's one of the, we used the OBSS on the station arm to get Perezinski out close enough to actually install the cufflinks and repair the tear in the solar array. So that was a real-world example of how the OBSS can be used in order to extend the reach of the station arm and get spacewalking astronauts, or to get spacewalking astronauts to points at the extreme ends of the truss that we wouldn't otherwise be able to reach. Another thing I'll point out is that on EVA-4, on this EVA, we're actually going to be removing the existing grapple fixture on the OBSS, and we're going to be retrieving a spare PDGF, power data grapple fixture, from another location on the station. We're going to install that PDGF on the end of the OBSS. So normally, as you saw in that video, the station arm can only grapple the OBSS in the center, which limits the reach. Once we do the work that we plan for this EVA, we'll have a PDGF on the end of the OBSS, so you get the maximum benefit of having the OBSS available to you. And let's see. In addition, we're going to basically some cleanup items at the end of this EVA. We're going to be taking some photos of the work that we did on the FGB PDGF, and also some photos of the FGB thrusters that have been requested by our Russian colleagues, and that will close out the EVA activities for the flight. Okay, Flight Day 12. We resume transfer activities. We do a standard rendezvous tools checkout on the orbiter side, we do a joint news conference with the crew, and then we have the farewell and hatch closure. And a couple of comments before I hand back to Gary. In parallel to all the activities that I described here, I hit mostly on the EVAs and the robotics. But in parallel to these activities, we're going to be doing transferring the items from the shuttle middeck that we brought up to the station. The other thing that we're working real hard on this mission is to get ahead on tasks required to support the next stage in STS-135. As an example, we've got an ATV attached that has not yet been completely unloaded. So we're going to do our best to get as much of that unpacking done as practical. We've also got some work that's required on the carbon dioxide removal assembly, or CDRA. So we're doing everything we can to make the 134 crew members available to do that work. So there's going to be a lot of stuff going on in parallel to the EVA and the robotics that I described, and that work is absolutely critical to making the next stage prior to the Soyuz departure and the time leading up to 135 work. The other thing I'll mention is that many of you may have heard that there was consideration and assessment being done for what we're calling a Soyuz flyabout. That was done on 133. A lot of the analysis was done of the station attitude required and the trajectory. We put together a basic timeline and what that would look like. In the end, they decided they weren't quite ready to do that on 133. We have been asked to look at that same thing for STS-134. My expectation is that the station attitude will be very similar, that the Soyuz trajectory will be very similar, that the objectives will be the same. We'll probably have a video camera inside the Soyuz. We'll have multiple cameras. And the intent there is to photo document the external of the station. And you know, with the shuttle flights winding down, this being the second to last one, this just represents a unique opportunity to get photo documentation of the entire configuration with the shuttle attached. So that's something you'll hear more about as we finalize the plans and look at the details. At a high level, what we would plan to do is use that +1 day that Gary discussed. He mentioned that we had a 14 + 1 day mission. We'd insert that +1 day in order to provide some margin to support this activity, and I would expect the Soyuz flyabout to be done later in the mission rather than earlier. You know, something on the order of flight day 12, 13. We haven't finalized what that day would be, but that's kind of what we're working towards. We've asked our Russian colleagues to look at this as well, and of course we need their approval and their final agreement to go do this before we would finish the details of the planning. But I just wanted to give folks a heads up that that's something we're looking at. And with that, I'll hand back to Gary to take you through Flight Day 12 and the rest of the mission.
Okay, thanks, Derek. So we're still on hatch closure day. Go ahead. We already talked about the 2 big payloads that we've transferred from the payload bay over to the space station. They're each just over 15,000 pounds each, so greater than 30,000 pounds of cargo that we transferred externally. The shuttle middeck's got well over 8,000 pounds of internal cargo that we're transferring over to the space station during the mission. And this, of course, is our last day to make sure we get the right cargo on the right side of the hatch. We're also bringing back quite a bit of cargo from station back down to the ground as well. So we'll be making sure we get all that accomplished here before we close hatches at the end of the day. And we'll also get the rendezvous tools and those type activities checked out in preparation for the undocking the next morning. So that takes us to Flight Day 13, which is undocking day, and flyaround, as well as the storm rendezvous day. So we have a video to depict some of those operations. Orbital will back away, undock and back away, and do a full 1-lap flyaround like we normally do. And it will do the nominal SEP-1 burn right there. And then the SEP-2 burn will put us on the storm rendezvous trajectory. So we're going to phase out above station and behind it. And storm will be taking data all the way out to the sensors drop block outside 20,000 feet. And then we'll go ahead and do a orbit lowering burn out here, which is going to bring us down below the space station and get us set up for the trajectory to mimic the Orion approach to the space station. And this approach is called a co-elliptic approach. So this burn down here is going to put us in a co-elliptic trajectory under the space station. And then we'll be catching back up to it and do the terminal phase initiation burn, which will bring us back up towards station. And it's designed to have us stall out at about 1,000 feet below and 300 feet behind the space station. And then orbital mechanics will pull us down and away. Storm sensors will continue to take data until the sensors drop lock. And when we get outside that range, we'll go ahead and call the dock mission complete. And then we'll start, we'll get our nominal water dumps accomplished and get ready to get the ship prepared to come back home. So that'll take us to flight day 14, which is the nominal landing minus 1 day activities. The entry team will come in, they'll do the flight control system checkout, make sure all those systems are ready to support the entry the following day. Do the reaction control system jet firings, make sure all the jets are ready to support the entry. And then, of course, we'll be doing all the internal cabin stow and reconfiguring to get ready to do an entry with the spacecraft. And then on flight day 15, we'll wrap up the mission with a deorbit prep and final landing of Endeavour, hopefully at Kennedy Space Center. And with that, we'll be wrapping up a very challenging and very successful mission, hopefully. And like we talked about, we got quite a few firsts on this flight. Really excited to be part of this and have the opportunity to take AMS to its final location, do storm activities for the Orion program, and test out a new pre-breathe protocol that'll be used for the rest of the life on space station. So we got a lot going on and really looking forward to it. And I think that's all we got, Kelly. We'll be ready to take any questions folks might have.
Thanks, Gary, and thanks, Derek. We'll move ahead to the questions. Please do remember to repeat your name and your affiliation before your question, and we'll start in the back row with Mark.
Thanks, Mark Carreau for Aviation Week. I have a couple of storm questions, and the first one is, when you undock and then re-rendezvous, how long will that exercise last?
Okay, I understand the question is approximate time duration it'll take from undock to the, call it the closest approach back to space station. I don't have the exact time off the top of my head, but it's on the order of about 3 hours and 40 minutes. And if you need the exact number, I can get that whole profile for you.
This is a follow-up question. Maybe this is a little philosophical, but this seems like sort of a significant test for the shuttle to do. It's always had a manual docking regime with the space station, and if I understand what Storm does, is it gives you in the future an automated sort of docking approach, which gives you more flexibility on crew complement, and I think this thing would even work with a lunar landing or an asteroid rendezvous. I'm not quite sure on all the capabilities, but it really seems to open some doors. And I just wonder what you're thinking, what your thoughts are on the significance of handing this off from the shuttle to a future spacecraft. Thanks.
Yeah, Mark, I think it's a outstanding way to take advantage of the spaceflight capabilities we have today, both the shuttle and the space station, to, like I said, demonstrate new technologies that will be used for all future spacecraft. And this capability it is being designed for Orion, but it is absolutely very applicable to any spacecraft that will be doing docking, like you said, in lunar orbit or Mars orbit, anywhere. So to me, it's a very significant progression of advancing technologies for future applications. So I'm very excited to be able to do this on this flight.
Philip Sloss with NASASpaceflight.com, also on Storm. How is that the choreography going to work on the re-rendezvous? Are you going to be doing burn targeting on the ground? Are you going to be using the storm sensors to do targeting, or are you going to be using the normal orbiter assets to do that?
It's a great question. The storm system is not integrated into the vehicle, into the shuttle vehicle, so none of that information can get into the targeting capabilities of the shuttle. So they're going to be basically operating separately from the orbiter. They'll be collecting data, and they'll be able to analyze that after we get it back from the mission. The orbiter will utilize its standard suite of capabilities. The rendezvous radar system will be our main sensor on the orbiter that feeds into the navigation system and will be used to target the first couple burns. I'm sorry, the first couple of burns are going to be ground targeted, and then once we get past the NH burn, we'll start targeting the rest of the rendezvous maneuvers on board with the sensors from the KU radar, and if we need it, we've got the star trackers as well. And but we'll be targeting the remainder of the storm burns with our standard suite of capabilities on the shuttle.
Bill?
Bill Horowitz, CBS, with three quick ones. One is on Storm again. What is the max range behind ISS before you start coming back? If you said that, I just missed it.
Yeah, Bill, actually, I don't think I said the max range, but that's a great question. We're going to, again, the sensors are right around 20,000 feet, so we need to get outside of that to give them an ability to get set up to characterize their acquisition performance. So the trajectory is going to take us right around 30,000 feet, about 29,000 feet behind the space station before we start phasing back in underneath and catching up.
Thanks. And two more for me, I guess, for Derek. On the Soyuz flyaround, this has to be Katie Coleman's crew, obviously, so they would come off of Rosfet, I'm assuming. And they were telling us last time we were discussing this, when it was a Poisk departure, that you didn't want to come off the bottom because there was some issue with pluming the tail of the orbiter while it was docked or it was inside that envelope. So has that been resolved? I assume it has, since that's what you're talking about.
We're actually targeting the Ron Guerin's crew for this flyabout. So they'd be leaving the Zenith MRM port.
Well, then let me ask about that, because I thought you would always use the departing crew in case something happened and they couldn't redock. You'd have the outgoing crew that would then return to Earth in that case. Why would you do it this way?
Well, it's all driven by what you described, the clearances and the trajectory from the Zenith versus the native ports. So ideally, you'd use the departing crew for what we're planning for this mission, just because the configuration of the Soyuz is, we would use Ron Guerin's crew.
Interesting. My last question is on Isle. Can you give us I don't know, scuba diving deep press bends 101 and explain how this works? I understand the camp out and how that achieves your goal. I don't know that I understand how Al does it.
Yeah, the intent of the protocol is exactly, or both the camp out and the out protocol exactly the same, as that's to cleanse the blood and tissues of nitrogen. For overnight camp out, with the crew sleeping in the airlock, the reduced pressure helps with that, helps the efficiency of removing nitrogen from the blood, and then that duration of the camp out also helps. And the goal is to minimize the time that you have to breathe pure oxygen the next morning. For Isle, what we found is that just by putting the crew in the spacesuit at the reduced pressure and then having them do some minimal amount of exercise. I should have mentioned that light exercise means barely moving in this case. It's not a leisurely jog or anything of that sort. It's just basically flexing your knees. And I think Allison has some video to show you just how light the light exercise is. So it's, I mean, the goal of both protocols is to get the nitrogen out of the bloodstream. They accomplish it in basically the same way by breathing an oxygen-rich environment at a lower pressure than ambient. But you're able to accomplish it quicker using the Isle protocol. If that makes sense.
Yeah. Well, I'll take your word that it makes sense.
Yeah.
Okay. Irene? Or why don't you go ahead and ask Robert, since he's closer.
Hi, Robert Perlman with CollectSpace.com. Just with a quick question about OBSS. The last time you stowed it on station and left it there, the sensors needed to be powered because you were going to reuse those sensors. Am I correct that they're not going to be powered this time and they'll just be allowed to freeze and die?
That is correct. There's no provisions on the S1 truss to power the sensor system on OBSS. So, in a matter of hours after we install it on station on EVA-4, the sensor package will have violated thermal limits and it will be assumed to be lost. And of course, there's no need for the sensor system on station. I mean, that's dedicated to inspection of the TPS, but that is a fact. Last time we left it, it was powered. This time it will not be.
Irene Klotz with Reuters. On the Isle, was that protocol developed to try and ease space station based EVA, since there won't be any more shuttle ones? In other words, are you trying to make things a little easier for the live-aboard crew? And also, will they be able to do a spacewalk, like in case of an emergency, quicker? Is that sort of part of the thinking that went into it?
Yeah, that's a good question. I mean, it's certainly a quality of life issue for future crews in that you don't have to take 2 of the 6 crew members and isolate them in the airlock overnight, which, you know, we go to great pains not to separate and isolate the crews from one another for obvious reasons if there happens to be an emergency. So not having them in the airlock overnight is a significant benefit. You know, it makes the morning or the evening before the EVA much more normal. It makes the morning of the EVA look just like any other morning. So, those are significant benefits. The other thing that ISLE helps with is that it uses less oxygen than the camp-out protocol. So, you know, down the road, looking at station post-shuttle, that's clearly a benefit. You asked about your ability to quickly do EVAs. The interesting thing about that question is that typically it's the planning required to get the crew ready that takes the time. Like if you look back at the pump module or remove and replace that we did in the last 6 months or so, you know, the time between the pump module failing and the crew going out the door was really all driven by procedure development and analysis and all the work that's required to understand the timeline and build the sequence. So, you know, I guess if you, in the event that you decided to do an EVA in the morning of, you could go do ISLE and be able to do it more quickly than camp out. But that, in reality, that would never happen.
And on the Storm hardware, could you just maybe explain a little bit about the similarities and differences between other things like the Dragon Eye that's been tested? And then also, just to clarify, Orion is not currently planned on docking at station, and this is just a way to use sort of station as a test bed and shuttle as test bed, since that's what's available to do these kind of in-flight tests. Is that right?
Yeah, let's see. The first part of your question is to try and compare with some of the other Dragon Eye and maybe TRIDAR, some of the other systems. Fortunately, I don't have the details of those systems, so I can't give you a good comparison. As far as using the space station as a test bed, absolutely. It's a fantastic way to, like I said, go ahead and verify this capability works and it is applicable to whatever we decide to do here in the years down the road. So it just happens to be designed and built for the Orion program, and that space capsule is actually developed and the hardware is available, and folks are, Lockheed's still working on that spacecraft, so it could still end up at space station.
Okay, Marcia.
Marcia Dunn, Associated Press. 2 questions. Do you expect a Soyuz flyabout decision before the mission begins, or might it drag into the mission like it did last time?
That's a hard question to answer. My hope is that we'll have a decision before the mission. If you look at the 133 situation, they didn't start talking about it until about 2 weeks before launch. So they had a lot of work to do in a very short period of time. I mean, we have the benefit of the work that they did to plan it, and we have more time between now and launch. So my expectation is that we'll have a decision before the launch.
And secondly, Endeavour's last flight, if you could maybe just touch on that briefly, and any payloads going up to commemorate that?
Well, of course, the last flight of each of these vehicles is very bittersweet for all of us that have invested so much of our time and careers into these flights. I've been so focused on getting this mission planned and all these details worked out, all our contingency planning together. I haven't spent too much time thinking about it. I know I have lots of time here starting in the summer to look back and reflect, but certainly it's going to be a bittersweet moment to see it back on the runway at KSC. And I'm sorry, the second part of your question was?
Payloads, you're taking up items,
Oh,
memorabilia.
Gotcha. Yeah, there are some special items going up. Unfortunately, I don't have that list with me, but there are things like patches, et cetera, that are going up to commemorate. And the crew's going to give a commemoration statement later in the mission that we'll provide to y'all.
Okay. Jim?
Can I go back to IL and explain a few things? You talk about partially suited crewman in a lower pressure environment, or is he wearing just the upper portion of the suit, and is he also presumably he couldn't be at different pressure than ambient in the cabin? Is he's breathing pure oxygen?
The way the protocol lays out, he does a standard 60-minute pre-breathe on pure oxygen, just like he would on a normal EVA day. And then we put him and his IV support crew, the 2 EVA crew plus the IV support guys, in the airlock. We depress at the 10.2, and then he does his suit donning at 10.2 in the airlock. So once he's in the suit and buttoned up and at the suit pressure, then we bring the airlock back to ambient.
Back up to
14.7 ambient.
Okay, so he's in the suit at 10.2, and you bring the ambient pressure up to back to 14.7.
Right.
And that doesn't have any kind of. He's got external pressure on the suit, and I've never seen anyone operate with external pressure on the suit. Is that any kind of mobility issue, or?
Nope.
Nope. It does fine. Okay, and so he's at 10.2. He's still in the proper O2 oxygen nitrogen ratio. It's not pure oxygen.
Correct.
Okay. You had me worried. Okay, thank you.
Yeah, and Allison's going to have more detail as well.
Hi, Clara Moskowitz with Space.com. A couple questions. The first one, with the potential Soyuz flyaround that you're considering, if you could just help me understand, if I'm correct, the reason it didn't happen last time was safety considerations, and how would those be different in this case?
Yeah. One of the challenges we had last time was just the time available to assess and plan it. I mean, it's a significant operation that we need to look at closely and make sure that we understand and do it safely. So one of the challenges is that we just didn't quite get there in time to make it work for 133. The other issue or concern identified by our Russian colleagues was that the Soyuz that would have been used for the 133 flyabout is a newer version of the Soyuz, with not as many miles on it, not as much flight experience. For what we're talking about on 134, we have the older version of the Soyuz, so those same issues wouldn't apply. So just to reiterate, there's nothing unsafe about the trajectory. The flying techniques are well understood. The crew will be well trained to go do it. For 133, we didn't quite have the time to finish the analysis, and there were some specific concerns about that Soyuz that we would have flown with.
Okay, thanks. And also, just with testing out of the ISLE protocol, is there a reason why that's not happening during the first 2 EVAs?
Yeah, that's a good question. There's not really a lot of science behind it. The thought was, since it's new and we might be surprised by things, we wanted to get a couple EVAs behind us before we used it. It's really as simple as that.
Okay. Any more questions on this side of the room? Do we have any follow-ups on the other side? Philip?
Philip Sloss with NASASpaceflight.com again. On the Port Sarge lube, how often do the race rings need to be, do they need this? If I recall correctly, both of them were done on ULF2. So, I mean, is this something that needs to be done periodically? And if so, when would the starboard race ring need to be redone?
Yeah, there are numbers. I don't have the numbers available to me here or in front of me. We can certainly get you those. I can say that the lubrication we're doing on this flight is earlier than called for, based on the analysis. So we're taking this opportunity to go do it because it's a relatively complicated task that it's nice to, well, it's a complicated task that it's nice to have a shuttle crew focused on to go do. And we're using shuttle resources for the EVA Vice Station resources. So we're doing it a little early because we can.
Bill?
Yeah, just a quick one on the ammonia refill. That's not something that can ever be fixed. I'm assuming periodically, then you're just going to have to do this over and over again to keep that thing topped off.
Yeah, it's a very, very slow leak, and there's really no good way to identify the location just because a lot of those plumbing lines are buried in the truss segment and you can't really get at. So if it continues, we would have to do this type of resurfacing again in the future. And the ammonia is available via the ammonia tank assembly. Right. We just have to do the same basic layout of the plumbing to get the ammonia there.
Okay, check one last time for questions here before we wrap up the briefing. It looks like no one else has an additional question. I want to give you a little heads up on the rest of our briefing schedule for the day. Of course, at 12:30 p.m., we'll have Allison Bollinger here, the lead spacewalk officer, to give you some more details about that and the ISLE protocol. At 1:30, we'll send the satellite out to NASA headquarters for today's video file. And then at 2 p.m., we'll be back with the STS-134 crew conference. Thank you for being here.